In this presentation, we're going to talk about geologic time. This should help you understand the chapter regarding geologic time and the accompanying lab. We're going to specifically talk about the difference between absolute and relative ages of rocks. The absolute age of a rock is where you give it a numerical value, like 1,000 years, 1,000,000 years, 10 million years. But when we talk in terms of relative age of a rock, we're talking about whether it's younger or older than the rocks around it. So here we go. Let's start with dating rocks using relative age, that is to say whether they're older or younger than the rocks that surround them. In order to do this correctly, we need to talk about a few principles to help us. The first principle is the principle of original horizontality, and this is simply the fact that sedimentary rock layers are almost always horizontal. The sediments that make the sedimentary rocks are laid down in horizontal layers. If you see sedimentary rock layers that are not horizontal, then they were tilted afterwards, probably by the process of plate tectonics. The next principle or law that we need to look at is the law of superposition. Again, it's very simple. And that is that rocks that are below other rocks must be older than those rocks. So the rocks at the bottom of a rock layer are the oldest, and the rocks at the top will be the youngest. A third principle or rule is the rule of lateral continuity when it comes to aging rocks. In this principle or rule, you can see from the diagram that when you see the same sequence of rocks on one side of a valley and another, you can assume that at one point they were all continuous, that they are the same sedimentary rock beds. In the case in this diagram that you can see that there's a valley that lies between the two tilting horizons, but we can assume that at one point these were together. In this fourth principle or law, we have the principle of cross-cutting relationships, which is purely logical. In this case, if you see one rock cutting across at an angle through another rock, you can safely assume that the rock that it's cutting across must be older, because it must have existed before it to be able to cut through it. For example, rock A must have already existed in order for rock B to cut through it. Therefore, B must be younger than A. On this slide, you see a cross-section of some sedimentary rock beds, an intrusion, and a fault, and using the principles that we just talked about, you can determine the relative age of each. First of all, if we look at the principle of superposition, we can see that the blue layer, layer C, must be older than B, which must be older than layer A. We can use the principle of cross-cutting relationships to see that C, B, and A must have been in place before that igneous intrusion D cut through them. And finally, we can see that E, which cuts through all of them, which by the way is a fault, must be the youngest. And so on this geologic diagram, we can tell that the oldest rock is C, followed by B, then A, and then igneous intrusion D, and finally the whole thing was cut through by fault E. Fossils are a very helpful way to determine the age of a rock. A fossil can be the remains or the traces, the clue that an animal or plant was once there. Sometimes you can actually find the body of a plant or animal, and sometimes you can find the clues that it was there, like its burrows or its, as it says here, fossilized coprolites. That's the feces of an animal, even a dinosaur. And sometimes you can find footprints. The process of a plant or animal actually becoming fossilized is called fossilization, and it's quite rare. Special circumstances have to be met. The plant or animal has to be buried quickly, and that would include any footprints or burrows, any trace of the animal too. Anything that's going to be fossilized, it happens quickly. The dead plant or animal is quickly covered by more sediments. Perhaps it was, for example, this fish fossil that you see here on the right was near a delta where there were plenty of sediments pouring out into the sea. Perhaps the plants and animals were subjected to a tsunami wave, and the tsunami wave pushed lots and lots of sediments on top of them quickly. Land fossils are much rarer, as you can imagine, because usually the plant or animals will decay right away. But they can still happen. For example, there can be landslides or volcanic ash. Maybe there's a sandstorm, or maybe mud in lakes that are on the land, or swamps or bogs, maybe even a tar pit, as in the case of La Brea in California. Here are some of the specific ways that fossilization can take place. For example, A, you can see an insect preserved in amber. Amber is just ancient tree sap. So that poor insect was probably, he had landed on a tree and got preserved in some of the tree sap, which later on hardened to become amber. In B, you can see petrified wood. This is where bone or wood is buried in sediment, and then mineral-rich water moves through the sediment and replaces the organic material with mineral, almost cell by cell. And so that sample of petrified wood, which you see in picture B, shows minerals that replaced the cells of wood one piece at a time. Kind of amazing. In C, you can see an example of a cast and a mold of a clamshell. And the cast shows the original bone or shell where it dissolved. You can see the shape of it. It dissolved away, leaving an empty space, and it was in the same shape as the clamshell. And later on, that space, that hole that was left, was filled in with other sediments or minerals, which created a mold of the clam. In D, this is a beautiful example of an ammonite that died and was then preserved by being preserved by the mineral pyrite. It was replaced by the mineral pyrite. And then E, can you see that there's like a leaf shape there, a fern? Well, that fern is a fossil caused by compression of the sediments, and all that's left is just a mere impression of where the fern once was. Index fossils are very special types of fossils. These plants or animals were only around for a short period of time. And so if we find examples of these, for example, this trilobite here on the right, If we find an example of this in a rock, then we can date that rock to a specific time. So we're at the transition between talking about relative dating and absolute dating of rocks. And in between them, we can talk about the geologic timescale. So the age of the Earth is thought to be some 4.6 billion years, and the geologic timescale is a way for geologists to organize all of those years into an easy-to-read chart. When they first put this chart together, they used relative age dating. So they knew that the Precambrian rocks were older than Cambrian rocks, for example. Later on, when absolute dating methods came into being, then we could apply absolute dates to the geologic timescale.